Hi everybody. Let's talk about section 2.6, which is the topic of related rate equations. And from now on, instead of writing all that, I'll just write RR. Okay. Related rate equations are an application of implicit differentiation, and they arise in engineering and sciences and stuff like physics. So I think it's a pretty cool topic to think about. A related rate equation is an equation that contains rates, and hopefully it only has two different rates. If we have more than that, we want to do something first so we can get down to just two. It just makes it more complicated. Here's an example. Let's say you have a circle that's growing over time. Okay? In this circle, there is a bunch of quantities that you can measure. You can measure the radius, the diameter, the circumference, and the area. Okay? As these circles grow or shrink, or as this circle grows or shrink, these quantities will change. Okay? The rate at which they're changing is their rate of change. We know their rate of change is represented by the derivative. All right, so we're going to use implicit differentiation to take the derivative of these quantity equations, and when we take that derivative, we're going to end up with related rate equations. Right? So here's the three rate equations that correspond to these three equations. If you blow this one up, okay, we can look at it up here. But before I do that, let's just talk about what we know so far and just add one different type of notation. Let's use Leibniz instead of Newton. Okay, so related rates, they're applications of implicit differentiation. Right, if we were to do implicit differentiation using Newton's notation, take the circle that we know, take its derivative with respect to the variable x. 2x. This y is a function of x. So 2 times the number in front, leave the base alone, reduce the power by 1, and take the derivative of the base function. The derivative of y, Newton calls y prime. And then the derivative of 16 is 0. Solve for y prime. Get y prime equals negative x over y. Do the same thing using Leibniz notation. Right? Now Leibniz uses dy dx for the derivative. And that comes from the fact that the slope of the tangent line is a definition using a limit. It's the limit of the slope of the line as we zoom in on that little piece of curve. So the limit as delta x approaches 0 of the slope can be written as dy dx. This is the rate of change in the y-coordinate with respect to the x-coordinate. That is our derivative. The derivative is a rate of change. So if you want to do implicit differentiation with Leibniz notation, it's going to look the same, but instead of writing y prime, we write dy dx. And then solving the same way, we would get dy dx equals negative x over y. Same thing, just a different way of writing it and just a little different way of emphasizing that this is a rate of change. So now back to related rates. That's a 5-minute video, so I'm going to stop and not make it too big.